Yes, thank you for letting me have this talk today. I'll give you 30 more seconds to read the comic because it's essential to what I'm going to talk about today. So, too small? Okay, so in short, download the comic sometime later on, it's funny. The problem with robotics, either in academia or also in hackerspaces or in your private lab or in your basement or whatever you want to do robotics, is that too many people start to reinvent what is already there. Of course, there are many reasons for that. I wrote them down in the talk summary. The API is bloated, it's deprecated, not using C++ 14 features, and so on. But still, I want to make a point that if you want to go into robotic projects in your hackerspace, have a look at ROS, which is well-established middleware for robotics, because it will give you many things for free that you would otherwise have to develop yourself, so that you can more easily get to the point where you actually want to work on. So, short overview, I'm going to give a technical introduction into ROS. I'm going to show some examples of technologies, packages that are already there and can be used out of the box in most cases, that do not only work, and this is where I differ from most introduction to ROS talks, can be also used with a webcam and a low budget. So if you have like, I don't know, 100, 200, 300 euros to build a robot, you can still use ROS to do it. You don't have to start with an Atmega or Arduino and program into registers again. And the last part will be about some tools that you might be missing from your custom implemented middleware that are really great to have, and you can have them if you use ROS. So first some text deserts, then some images and funny videos, and at the end some hyperlinks. So if you do robotics, what are you actually doing? Robots mainly consist of 3 parts. So you have some mechanical parts, some electrical parts, and software. Today I'm only going to talk about software. There's also many interesting projects how you can build modular reusable hardware, not only software, but today it's about software. So what kind of software is in a robot? Of course, there's drivers, cameras, motors, whatever else there is you want to connect to your robot, LEDs and so on. Then there's some core robot functionality. You want to be able to do path planning, motion planning. You want to do some kind of image processing, 3D reconstruction from stereo cameras, and so on and so forth. This is what I call core functionality here. Then usually your software does not run the way you want it in the first place, so you need some debugging facilities, also introspection. Your robot is doing something you did not expect. Instead of just hitting the emergency stop button, please always add one to your robots, you can have a look what is currently happening within the software if you did not build a large binary blob that you are flashing onto your robot. Then you need all kinds of algorithms. And here is where most academics work on, like myself. You want to do, I don't know, motion compensation in cognitive surgery with robots or whatever. In any case, you need some very basic algorithms. Otherwise, your robot will only like move around rather randomly. So if I want to make my robot grasp this microphone, I need to do motion planning with my many degrees of freedom arm. I need to do grasp planning. I need to do collision avoidance and all of these things that are really hard problems. People are working on them since like 30 or 40 years. They are not completely solved yet, but they are very good open source implementations that solve it for the usual cases. And the usual cases, fortunately, are the ones one usually encounters. That's why they are the usual ones. Then once your software gets large enough, you will not be able to run it on a single machine anymore. May this single machine be some embedded device like a BeagleBone or, I don't know, a CTEC box or what all other ARM boards there are around these days, not even an i7. You usually want to be able, if the computation demands it, to distribute your robot software to multiple computers that are connected via Ethernet, for example. And all of this is already built into the core of ROS. So everything I'm going to show today can be run on my single laptop. Most things can be even run on something like the new Raspberry Pi. But it can also be started on a cluster of computers. So if I have like 5 desktop machines available, I can put the camera processing on one machine, the path planning on the other, and it will work together the same way as if it would be running locally. And that is completely networked, transparent, and happens during runtime. Then this is also, if you have multiple machines, you know that it's not as easy as compile, run it, because you have to distribute it to the various machines. You have to start the components on various machines. So deployment and orchestration is also something you need to take care of once you have more complex robotic software. And of course, it's taken more or less care of already. So what do you want to work on? Usually this. You want to build a cool application, I don't know, have a robot that gets the pieces out of your freshly built 3D printer so that it can continue printing instead of you having to go there, take the part out and click on to print next one. So, but where you usually end up working on is the very low-level software. Get the motor to turn, get the motor to position itself at a certain degree, get your camera running, get your camera data into OpenCV, back out of OpenCV, create point clouds, use the PCL and whatever. So you are doing a whole lot of plumbing work when you are working with robots, and this does not have to be the case. That is what I want to show now. So what is ROS? ROS stands for Robot Operating System. It consists of 4 major parts. One is the middleware together with tools. Never underestimate the importance of having tools available for whatever you're using. Then the basic robotic software, distributed processing of coordinate transformations. So for example, if you have your robot and you want to tell it, move 5 centimeters to the left, you usually specify that within some kind of coordinate frame. So either it is the coordinate frame of the robot, it is the coordinate frame of my laptop, and so on. And you, in the background, you do just some matrix multiplications to get everything right. Perhaps you remember your algebra classes or not. It does not matter, because here it's just an API call. Give me this position in this coordinate frame, and it will do all the magic algebra in the background. Then the third, and I think most important part about ROS, ROS is not better than any other middleware that was built, and there were hundreds of it in the last 30 years, but it gains such a big momentum that a large ecosystem formed around it, kind of similar to Linux, perhaps, compared to the BSDs. Now don't feather me for that. But the important point is you can take ROS today, install it, which is easy, apt-get on Ubuntu's, and then have a large collection of software available that I will be showing shortly what is already there. And these are the 3 main components that make ROS a great tool to use for robotics. So now I'm going to describe some of the technical terminology used in ROS. So first, there's the ROS core, which is the only centralized part of ROS. So it's a well-known instance, like your name server, for example, and it can point you to the other instances within your robot network. Nodes are any process within your robotic network that implements the ROS client API, which is usually used through ROS CPP or ROS Pi, which are the main programming languages used to interface with ROS systems. There are also many other interfaces, even for MATLAB these days. Even officially from MathWorks for MATLAB these days. So it really got important, obviously. And these support all the nice features I'm gonna show till the end of my talk. So initially you start out with an empty computational graph. So basically we are talking about nodes and edges that connect these nodes. So the node is some kind of process on an operating system running on any machines that are connected to your ROS network. And then there's the central ROS core running on one of these machines. So initially there are no connections. We have just started the ROS core. Then we add a node A, and A wants to publish some information under the name some topic. Either later on or previously, timing does not matter here, node B comes along and wants to subscribe to this some topic. And so it also tells the ROS core, please tell me who is publishing information under this name. So it's a classical publisher-subscriber architecture for those people who read Tannenbaum. The ROS core answers with the IP address and port of this core, so it's all based on TCP/IP. There's also UDP implementations, but the standard is TCP/IP. After node B knows about how to reach node A directly, it will contact him. This is all XML RPC. And from there on, node A will transmit only the bulk data to B whenever there's something new that it wants to tell its subscribers about. So as you can see, the ROS core only gets involved into setting up the connections, but it's not a central bottleneck in the network. So not all of the information is pushed through the ROS core, which is quite fortunate, because if you have a couple of Kinect cameras, for example, on your robot, each one saturates your gigabit link. So you really do not want to add artificial bottlenecks too. And the nice thing about this architecture is that on the same topic, any number of publishers can add information to this topic, and any number of subscribers will be informed once there's new information available. On a technical level, this is done at the moment with unicasts, so you have multiple copies on your network, but in May of next year, it will also be able, or at least that's the plan, to use IPv6 multicast. So then it's even efficient what you're doing here. So topics I already introduced, those were the names under which information is published. So it's just some way to define where to find the information, and it's built up in a hierarchical structure you'll see shortly. So you can kind of imagine it like your URLs in your file system. Your file, whatever funnycatvideo.avi, is located in some directory, and you can refer to it under that name. So these are the names in ROS, but they are not locally, but used within this ROS network through the ROS core. A topic is a unidirectional connection, so you publish information and people subscribe to it, so it's not bidirectional. So you do not get feedback on who subscribed to it, and you don't care about it. You just publish it, and if there's at least someone who's interested in it, this node will get the information. There's another kind of IPC inter-process communication mechanism that are called services, that are your classical remote procedure calls. So you call this name, pass some parameters to it, it will be serialized through the network, the destination node will do some kind of computation, answer with reply, and afterwards this kind of communication is ended. So it's not intended for streaming data, it's more for like, please reinitialize yourself, or please do this calculation for me, or get me your current set of parameters. And the good thing about these communications mechanisms is that they're kind of complementary. So you have your topics for streaming data, sensors, think of a camera, or your robot, which publishes its current position of all of its ankles and joints. The problem with it is that messages may be dropped due to overload without notice. But if you think about it, if you have a camera publishing information each 33 milliseconds, like at 30 frames per second, you really want the frame to be dropped instead of a queue building up if your Wi-Fi is too slow and you go further and further back into the past and get a large latency. So that is why it was built with loss in mind. Services, on the other hand, are blocking calls. So you call a service, get blocked within the current node, will be transferred to the distant node until the reply is received, you are blocked, which is nice to do some kind of tasks. And then there are also actions which build on the first two mechanisms, and they allow you to deal with long-term tasks. For example, if you tell your robot, move from here to here, you really do not want to have that as a function call, like in your programming language, because it will take time until the robot goes from some point to another point. and you might want to get feedback in between as well. So with actions, you tell your robot, go there, and then you are unblocked when this request was received by the other node. And then you can get intermediate feedback, and in the end, you get the result. For example, okay, I reached the position, or I collided with your cat, or whatever. And all these kinds of mechanisms are used in what I'm going to show further on. The last terminology I have to introduce are parameters. So the ROS core also acts as parameter server. You can kind of add, it's a bit similar to REST APIs. You can just add names there with some data attached to it, and also with various kinds of data. So not only strings, but also arrays, whatever you can serialize in YAML. And this is usually used to do distributed parameterization of your nodes. Imagine you have the classical solution of configuration files, and you want to run your node today on a different machine. Then you would have to make sure that your configuration file on this machine is up to date. With the parameter server, whoever in the network starts this node pushes the current set of parameters to the server, and all nodes, no matter on which machine they are running, uses these parameters to set up their algorithms, for example. Okay, I talked about names. For everyone who ever used URLs or perhaps a Unix OS, it will be quite familiar that you have absolute paths that begin with a slash, and you have relative paths that are not anchored kind of at the root of your system. And this is quite nice because you can, at runtime, tell a node, okay, don't publish your topics at the kind of the root of your namespace, but push it one space down, like kind of moving something into a subfolder. If you have relative addresses, everything will continue to work within that subfolder, even if you push it down. So for example, if you have two webcams, you simply start your driver node twice in separate namespaces, for example, camera left and camera right, and the software does not need to know about that it currently is being used together with another camera. That is just a runtime decision when you start your nodes. So a small example, here we have 3 nodes within our network and our ROS core. For example, we have the UVC camera node publishing images from some webcam. We have some processing node that does, for example, an edge filtering with the images. And then we have our RQT GUI, which displays these images for the user to look at what the robot is currently perceiving. So we have here our parameters. We have our nodes, we have our services that can be used as RPCs, and we have our topics where streaming data is moving. Now we have all kinds of tools for all of these things I talked about. There's the command line tool that allows you to have a look at what is currently running into your network. For example, if you want to find out all the nodes that you've started on your various machines, you just type in your command line ROS node list and you'll get the list, and you can get additional information on each node. The same for topics, services, messages for the different data types that are used. For the parameter server, and also their 3D or GUI and 3D tools you can use to view the current state of your robot. You'll see them in a short bit. So just here to glance over, these are 2 code snippets, one for Python and one for C++, to publish something on the ROS network. So it's quite simple. You initialize your node, you create a publisher, you fill your data type with information, and then you call publish, and you don't have to do anything else. Then it will be already available. If you type ROS topic list, you can already see a topic as a new topic available. And if you go to the next slide, you can write your subscriber with a few lines. You create the subscriber, tell it what is the name of the topic it should subscribe to, what data is being sent on it, provide it with a callback. So this is event-driven. And afterwards, this callback will be called whenever some node on the network publishes something under the name a topic. And that's about it you have to know to use most parts of the middleware of ROS. Okay. Yes, ROS has its own build system, as perhaps all large software frameworks have come up with. The good thing is it's only a very thin wrapper around CMake, so if you have ever worked with CMake, you will be fine. Otherwise, learn CMake. But don't worry, this is really no game changer. It's just you have to look at what is written on this slide, and this slide, and then you are in CMake world again, and it will take care of resolving the dependencies between the ROS packages you're using, that they get built in the right order. So it actually helps to work with it. Also, it's of course annoying. But I've never seen a build system that's not annoying, so no change here. Okay, so now I've talked about what ROS is in technical terms. So what do you need to use ROS? Do you need always an i7 PC? Perhaps you don't have one on your quadcopter or on the International Space Station, both places where ROS is currently running. No, you simply need anything that can run Debian, Linux, or preferably Ubuntu. So I'm saying Ubuntu 14.04 here because that's the easiest way. There you just type sudo apt-get ROS, whatever, and it's installed. You can, of course, build it from source on all other platforms, but I don't think you want to. It has a couple thousand dependencies. So what kind of machine do you need? Preferably some powerful desktop or laptop machine so you can get started. A good solution if you are power constrained is to have a small machines on board of the robot, like a BeagleBone or a Raspberry or an Intel NUC, and a faster machine of the robot that does the heavy processing. But you can always, as I said, use it locally and you don't get a large performance penalty. But it depends on what application you're running. Of course, if you have like 4 Kinects that stream data and you want to do point cloud processing on them, you can put some desktop machine into your rack for each Kinect, because that is just computationally intensive. If you just want to have a mobile robot like a Roomba moving around, it's probably enough to strap a BeagleBone to it. Okay, now let's come to the part with more images and perhaps more interesting if you are not yet sure you want to use ROS. So for all the usual kind of camera sensors you find on a robot, like mono cameras, for example, a single webcam, stereo cameras, for example, 2 webcams, and RGBD cameras, for example, a Kinect or an Asus Action or Xeon or whatever you want to spell it. You need drivers for all of these. You need to calibrate them intrinsically and extrinsically. You want to visualize what's currently happening, and you need processing so that your raw data do something useful for your application. And now I want to go through all of these steps for all 3 camera types very quickly. I'm not going to talk about object recognition here. There are some ROS-specific frameworks to facilitate object recognition, but basically they come down to using OpenCV and the point cloud library. But still, it might be easier if you want to do object recognition to look what is already there in ROS, what packages have been built by others, instead of rolling your own from the onset. So let's define a launch file to start my webcam. Launch files are just a convenient way for deployment and orchestration. It's just an XML file starting with the highest level tag launch. Then you can add any number of node tags where you simply tell ROS from which package, what to load, what process or what binary. You can give it some name and define some parameters. For example, here I said namespace cam, so everything will be pushed down into the subfolder camera so that I don't have a whole mess of topics at the top level namespace. And then you add some parameters for specific, of course, to your node, the resolution of the camera, frame rate, disable autofocus, and so on, and that's about it. Then you type ROS launch. I prepared screen capture videos for this because live demos, as we saw in the previous talk, are always too dangerous. So let's have a look at this. I hope it works. So I started my ROS core. This is all on localhost. I'll start the launch file you just saw. Then I run the RQT GUI. no, I'll just, okay. First, want to have a look on the command line. I don't like GUIs. So let's have a look at the command line, what nodes I've started, what topics they created. That's all good and all nice, because you can also get more information about the topic, number of publishers, what type the topic has, and so on. But no, I just started a camera node, so I might want to see the camera images. That is where I start the RQT GUI. Here I select as a plugin visualization image. And then you can have a drop-down menu, which gives you all the choices of topics that carry sensor messages image as their type. So these are normal two-dimensional images in ROS. And I can just select that and have a live view of my camera data. And this is during runtime. So I did not have to recompile my camera driver node, adding debug output, for example, OpenCV image show. I just can at runtime start my GUI, and it will connect as a subscriber to my data stream and also get a copy of the information. All other nodes keep on running. And this would have been working exactly the same way whether I started the camera locally and the RQT GUI locally, or one of those remote and the ROS core on a third computer. Don't ask about security. ROS was not built with security in mind. So the first thing you should do when you start to use ROS is do sudo IP tables -flush, because otherwise you will have very weird connection problems within your ROS network. So you might not connect it to the internet during that time. Okay, now we have a camera. Who has ever worked with image processing here in the room? Perhaps raise your hand if you've ever done some kind of image processing. Okay, so then a short reminder, if you have a camera, you need to have a mapping between the pixels and the outside world. So if you just have the image, you do not really know a relation between pixel values and SE units. For example, you do not know how large is this object 5 meters away in pixels if you do not have an intrinsic calibration of the camera. So intrinsic calibration gives you a mapping between the outside world in terms of meters to what you get from the camera in terms of pixels in a very simplified manner. There's a utility for that. It's using OpenCV, but if you've ever wrote your own OpenCV calibration for camera software, you know that there are many weird corner cases and so on, and it's really nice to simply have a GUI for that. I'll show you the video and then... So basically, we have everything running from the previous screen capture. Now I additionally start this calibration node, which will give me a GUI. And now if I update on the left hand the plotting of my ROS graph, which is also a very nice introspection utility that comes with ROS, you can ask ROS to plot itself. So to tell you which nodes are running on which machine, who is connected to whom, what amount of data is being transferred in between, and so on. So now that I started this calibration node and I update this graph, it appeared here as a node subscribing to the image, of course, of the camera and outputting to the ROS out. Okay, then you do the usual thing, run around in front of your camera with a checkerboard. Don't have to watch that. And then in the end, you get this screen where you are told whether you have enough poses of your checkerboard captured, which OpenCV does not tell you by default. So it's again a nice tool to have available instead of writing your own. And then finally, if everything is green, you hit calibrate. It will do the intrinsic calibration using OpenCV, and you get the camera metrics, the distortion coefficients, the projection metrics, and so on. So for those of you who know what it is, fine. For those that don't, doesn't matter. You have your camera intrinsically calibrated, and you can use that downstream. And it will also automatically start a topic that's called camera info, and there you can get the parameters of your camera, and this is used in all different parts of ROS wherever you need the mapping of cameras to external values. What is also written down here on the command line with the colon equal sign is runtime name remapping. So the camera calibrator Pi, if you look into the source code, it subscribes to the topic named image. And now I would have to go about and change this string in the code in order to change to camera image raw, because that is what in my ROS network on my robot the image is called, or what is the topic under which the image stream is published. But the nice thing about ROS is that you can do these remappings during startup or even during runtime, where I just tell this node, okay, whatever is called the name image in the ROS network for you now is camera image raw, and everything will start working. So that's really nice way of flexibility in your software, and also how you can write quite modular, meaning loosely coupled nodes, because they don't have to know about each other upfront. They just talk to each other using standardized formats, and the namings, the topics on which they talk, you can specify at orchestration time. Okay, then once you have your camera calibrated, you might want to do some post-processing. For example, if you have an industrial camera, usually it does not output color images, rather it does output grayscale Bayer images, and you have to reverse the process and so on. And for all those low-level processing steps, there are nodes available. You just start them, and they take the raw data as input and output the process data, and you can connect your higher level algorithms with these data streams. If we want to write our own processing node on ROS, so we want to take in an image as input data, we want to apply some OpenCV filter, in this case an edge filter, and we want to output this data to our ROS network, perhaps to be used as input by a higher level processing node. Furthermore, we want to be able, during runtime, without restarting anything, to change the parameters of this filter we are running on the input images. And this is called dynamic reconfigure in ROS. I'll show you a video how all of this works together. So I'll start the node I programmed. If I update again my ROS graph, it will show up as a new node subscribing to the image topic. And now I have available a new topic with edge filter applied to it. And then I can start in RQT GUI, the dynamic reconfigure plugin, where I get all these parameters I defined as being dynamically reconfigurable in my algorithm. And I can play with them during runtime. And this is all something out of the box available. You don't have to sit down and write a library that can do something like that for you again. And this is really nice to quickly get to something that does something interesting from a point of view of the application. And all of this takes just 36 lines of C++ code. I think this is quite few code in order to have something that's network transparent, that can be dynamically reconfigured, remapped at runtime, and so on. So it might be better than linking libraries to each other to change something. Okay, so we had monoscopic cameras. Now let's do stereo view. Like we humans, we have two eyes, so we can process the disparity. For example, I see this microphone more to the right of my right eye than to my left eye. And from that, I can triangulate the three-dimensional position of this microphone. And also you can do that with robots. And you usually want to perceive the world in 3 dimensions in order to figure out where can the robot move along, to do object detection in 3 dimensions and so on. So again, we write a launch file. The node this time is called UFOZ stereo node. Those are all available. We again add some parameters to it. This time we have 2 devices, a left camera and a right camera. Define which webcam is attached to which Linux video device. And then we can start it we have this node, it publishes 2 topics under those 2 names. We can again start RQTGUI and have a look at them. If we want to do stereo calibration, which not only does the intrinsic calibration, but also correlates what the right camera sees to what the left camera perceives at the same moment, and also does synchronization and some other algorithmic transformations of the images. And there's also this calibrator node for it, pretty much looks the same way as previously for the mono camera, only with 2 images. Okay, once we have our stereo camera pair calibrated, we can use the stereo image proc to reconstruct a 3-dimensional colored image from our 2 cameras. And all of that this takes is a launch file with about 5 lines of XML in addition to what we wrote down to start our cameras. And this node also has available a dynamic reconfigure GUI in order to change the stereo reconstruction parameters. So if you get into stereo reconstruction, you know there are a whole lot of parameters you have to set. You can do that during runtime and don't have to write a single line of code for it. And then the result are point clouds. And point clouds are a really nice format because there's the PCL library available, which does what OpenCV did for image processing for point clouds. So a really large, close to state-of-the-art library with all kinds of algorithms that allow you to get with only a few lines of code to something that's applicable to what you actually want to do, instead of writing low-level, take this point, compare it with the one to the right and do something. Okay. Then the last kind of cameras are the Kinect-style cameras. Unfortunately, the Night was bought by Apple and they closed it down, which is a bit unfortunate because those devices replace in academia research for, I think, 150 euros, replace devices that cost about 20,000 euros, and they're good enough compared to laser rangefinders and so on. And to start this device, have the point cloud available, you just type in this line at the command prompt, you start a launch file someone else has written for you, and then you get a point cloud you can process in your network. So let's have a look at this. So this is the RGB image from this R16, this is the dev image, which is all quite nice. But what you really want to have, if you get a point cloud out of something, have a look at the point cloud and do it interactively. And this is what you can do with Arvis. So you just start Arvis, add this point cloud plugin to it, tell it on which topic to listen, how to do the color transform, and then you have 3-dimensional point clouds introspectable by the human developer who needs to debug what's going wrong at the moment. And writing something like this viewer by hand, I can tell you, takes you more time than you planned to spend on your whole hobby robotics unload my printer project. So perhaps I have a few minutes time to trying to do this live. So let's start our ROS call. Let's ROS launch. I'm not sure if it will be working because my laptop has not really enough power for this, but we'll see. Okay, that's... So now I add this plugin that's specifically for point clouds. And of course, it's perhaps not working. Okay, I won't spend too much time on it. Perhaps let me have one look at the driver side of things. Ah, okay, I forgot to check register dev images. Ah, there we go. So perhaps I should look at something that's not out of range of the camera. Ah, there we go. So now we have a 3-dimensional view here of our wall. Okay, and this was without writing a single line of code, and also you can do all the other nifty things I talked about to it. Okay, that was the wrong key. Yeah, obviously PowerPoint and connecting beamers to laptops is more complicated than robotics these days. Okay, where did we leave off? I think that was here. Okay, and the nice thing about it is if you have a stereo camera pair and a Kinect on your robot, which is a quite common setup, they output the same kind of data format, so you can switch in between your Kinect style device and your stereo camera pair, and this is highly valuable because Kinects are much better at reconstructing what is in the range of like 0.5 meter to 4 meters, even in the dark. Stereo cameras obviously need light, like ourselves, to see anything. But on the other hand, they're much better at doing long distance reconstruction. Or if there would be sun shining into this room, okay, I know this doesn't happen at hackerspaces, but then Kinect style cameras do not really work well. So if you have your middleware set up in a way that it does not matter where you get the input from, you can just at runtime switch between the two devices that feed you the data, and all your higher level algorithms, for example, collision avoidance, will continue to work the way they did. Okay, now I was talking a whole lot about sensors. So cameras are obviously only one example of sensor you might find on your robot. There are drivers for laser scanners, for laser line scanners, for distance sensors, for what I do not know at all what there is these days. There's a listing on the ROS wiki page. The link is at the end of the slides. Have a look, perhaps your device is already supported. Otherwise, ask me. We implemented quite some drivers, for example, for the RGBD LEDs, the WS812, what are they, 8216 or whatever. Those LEDs you find a lot of in the basement. We have a ROS driver for that, so just connect them to a BeagleBone and you can have a display with ROS. So it's also, ROS does not only work nice for robots, of course it is targeted towards robots, but whether you are looking for a flexible middleware that does not need hard real-time constraints, and if you don't know what hard real-time constraints are, you might not need them. So if best effort is good enough, so if you can just check whether your data is being processed fast enough, and if it is, it's fine, then ROS is quite nice for a whole lot of hacker and maker projects. Okay, but now let's get into robots. We want to model our robot. For this, there's an XML-based description format called URDF. You start out with the top-level tag robot, give it a name, then you add links. Links are the rigid objects that connect joints together. Like, for example, if I want to model my arm, perhaps I could model it as 2 links and 2 joints in between the shoulder and the elbow. And then you have to give them a visual appearance. This can be either geometric primitives or meshes. And meshes are nice because you can create them with Blender, you can export them from your CAD application, and you can just tell here, use mesh for this link, and it's there. And this way you can easily either model your robot before you build it, which is quite nice, because then you can explore its kinematics before you find out they're wrong. Or you could just model your robot to do all the things I'm going to show in the next 10 minutes. The links are connected by joints. They are different types. So if you have electrical motor, for example, a servo motor, this is type revolute joint. It has joint limits. You cannot move it endlessly in one direction. And you specify all of these kinds in here. Okay. Once you're done with that, you might want to have a look at it. And again, the nice thing about it is other people already built software so that you can focus on what you're interested in. So I wrote down, that's about, I think, 100 lines long, the description. And now here's my very simple robot consisting of 3 links, a base cylinder, and 2 arm segments connected by 2 joints. And I can immediately move them around without writing any code through this GUI. And this way you can also explore how you want to build your real robot. For example, if you go the usual hobbyist way and use servo motors and aluminium profiles to build it. Okay, now comes something really cool. If you have a robot that has a couple of joints, it gets really complicated to define in which position which joint has to move in order for the robot to get to a certain point. This is the problem of inverse kinematics. And usually you do that by calculating something called the inverse Jacobian matrix. That already sounds like a lot of math. It's much more than that. And you might not want to get too deep into this if you just want to unload your 3D printer, right? So there's something since, I think, the beginning of this year called the Move It Setup Assistant. And you just feed your robot description into that. It creates some nice GUI where you can load your robot. Again, it's immediately visualized. Writing such a GUI, again, has taken some people, I'm very grateful for that they did it, a lot of time to do that. Then you do all kinds of configuration, but it only takes you about 2 to 3 minutes. Can more or less use the default parameters. If you have a robot with multiple arms, you define which kinematic change are planning groups and so on. And in the end, you store all of this. This is very well described. So this talk obviously is not a tutorial. You can just look at the website. It's really easy to figure out. Okay, afterwards, you have your kinematic description of your robot, and you can use this. They provide a demo.launch file for each robot you have exported from the GUI I just showed. And with this, you can do something amazing out of the box. You start this demo launch file. It starts Arvis for you. There's your robot. And you can immediately do motion planning with it, with various state-of-the-art sampling-based motion planners. So for example, now I just told it go to some valid position, and now it planned a path to go there. Of course, this seems trivial with such a robot, but if you have a robot with 6 degrees of freedom or even 7 degrees of freedom, you really can't do that in your head. It's very, very counterintuitive what these joints are doing in order for the robot to simply move along a straight line in our Cartesian 3-dimensional space. And here you get it out of the box. And the nice thing is, this is now just a dummy robot, but if you would connect your servo motors to a controller, do some low-level setup so that you can specify what number do I have to send where so that your servo moves into this position, you can immediately use this GUI to move your real robot, to do path planning with your real robot, and you can even put a Kinect next to your robot and do collision-free path planning using the Move It framework. So this is really great that this is available nowadays. That took, I know of many projects in academia that took like a year just to get this basic motion planning running stable and reliably with their robots. And now you get it like in 10 to 20 minutes, which is then a whole day if you consider debugging. But that's really, really a large improvement. And if you hate GUIs, that's fine. Everything I'm showing is well separated between the GUI components and the code. So if you want to do path planning, not through a GUI, but from your code, because you recognize an object in your image, of course, there's a Python and a C++ API to tell the robot, okay, go to this point. You don't need to go through the GUI. Okay, if you want to go even further and want to simulate your real robot or your robot you might want to build someday, there's Gazebo for it. Physically based simulator that's integrated quite tightly with ROS these days. And there are a couple details I'll leave out due to time. There are different formats, but you can convert them in the end. And since ROS is built the way I told you about in the beginning with the topics, the dynamic renaming, and there's a mechanisms for us to not use the real progress of time, like what we call wall time usually in simulation world, but your simulated time. So if your computer, for example, is too slow to run the simulation in real time, so it is only can progress with 30% of the speed the real world time progresses, all of your ROS nodes will automatically adapt to that. So if you say sleep 10 milliseconds through the ROS API, it will sleep either 10 real seconds or 10 simulated seconds. Dynamic, all by itself. You don't have to recompile anything to run your nodes against simulation or on your real robot. And of course, you can do all kinds of software engineering, test-driven development, continuous integration. There are people who integrated this with the Jenkins server and so on. You can do distributed development in your hackerspace because perhaps not everyone has the same robot available. You can still develop algorithms, test them on the simulated robot, and then once you're back in the hackerspace, test it on the real one. Stay close to the E button in that moment. Okay, let's assume we attached a webcam and an RGBD camera to the robot we modeled earlier and converted the formats into each other. Now I started the gazebo simulator. I add this robot here. And now there's a physics engine in the background. So you can throw objects around, and if they hit each other, it will happen more or less physically plausible. So they're using different game physics engines like Oat and Bullet in the background. And so I could flip over this bookshelf if I hit it hard enough in the simulation. So you can really do some kind of advanced manipulation. And as I said, we just added a simulated camera, and you can get images from the simulated camera in the same manner you get it from the real camera, which gives you opportunities to do for what I started to call robot unit testing. So you can use your software one-to-one as you use it in your real robot, run it against a simulated environment run it against a simulated robot within a simulated environment, and thereby ensure that if you change the code, nothing breaks, and nothing, not only on the level of it still compiles, but on the level of the robot still does the correct thing. So okay, here's the simulated point cloud again. I have to skip ahead. Debugging tools. I showed you the command line tools. I showed you a tiny bit of the plugins of the RQT GUI and the RViz 3D visualization. Now we are at the Outlook. So I talked very, very brief about Gazebo and Move It, simulation and motion planning. There's a whole new framework to do low-level control, for example, control loops, PID control, and so on. That is already integrated with ROS. So if you use ROS control on your microcontroller to get your motor to stay in the correct position, if you tell it to, it can automatically interface with Move It, with the visualizations and so on. This is really nice. So perhaps have a look at it in the beginning and then start implementing instead of the other way around. And yeah, of course, OpenCV and the PCL are two talks for itself. Then there's also the possibility of using shared memory transparently within the same host instead of using local loopback. For efficiency reasons, there's GPU processing. You can do SLAM, simultaneous localization and mapping, which means you put your robot here, it drives around. While it drives around, it builds a map and localizes itself within the map it just built. And this is a really huge scientific research question for the last 10 years. And now we have open source software that does this reliably for indoor scenarios. So basically you have your Roomba, stick a Kinect to it, configure the navigation stack, and you have SLAM, which like many, many PhD students worked hard on for the last decade. Okay, of course you can integrate beamers for augmented reality, like project something onto the robot. Okay, that now I'm really out of time. There's NoROP, so if you want to do knowledge processing, artificial intelligence, ontologies, all kinds of world perception, world understanding with ROS. The people from the TUM have worked on that quite a while. Have a look at these two pages, what people are already using ROS for. ROS 2.0 is coming up next year. I hope this will be great. The negative thing about it is it will deprecate some things. And as you know, if something gets deprecated, the person who once wrote it might not be there anymore to fix it. So there might be some breakage, but they're basing ROS on a much more solid middleware. So it will everything will stay the same from an API point of view, from a user point of view, but as the lowest level, they will be using DDS, data distribution services, where you can add real-time guarantees, channel resources, and all other kinds of things. And the transparency between network-based communication of nodes and shared memory-based communication of nodes will be completely, so you don't know whether you run your nodes on the same host, it will use shared memory. If you run it on multiple hosts, it will do network serialization. So this will be great. If some of you will start working with ROS and help make it great, that would be even better. So, and I thank you very much for your attention. I hope someone will read the line at the very bottom. If you use ROS for any of your hobby projects or in your hackerspace, plan to use it now or just got interested, find me at the Congress, talk to me. I'm really interested to hear what other people are using ROS for, or just send me an email if you don't catch me here. Thank you.
Okay, thank you, Andreas. So far, we still have maybe 1 or 2 minutes left for a few quick questions. If anyone has a question, and just come to one of the Saal microphones. Okay, so that doesn't seem to be the case then. Thank you so much, Andreas. Thank you for listening and attending.